Let's look at a PhET simulation of a bar magnet. You will notice on the right here I have a compass. Now the compass is, if you'll notice, the needle begins to move as I move the compass around. The motion of the needle follows the field lines that are displayed for this bar magnet. Now notice how the white point of the compass is pointing towards the North Pole. That means that the white point is the compass South Pole. Now notice if I move that to the other side, the South Pole of the bar magnet attracts the red point of the compass. The red point of the compass is the North Pole of the compass. Notice if I move outward from the bar magnet, it follows the field line directions for the behavior of a magnetic dipole. And I can also do other options over here if I wanted. For instance, I flip the polarity. Watch what happens to the compass needle. Now the compass needle is flipped over because I'm now going to orient the North Pole of the compass to the South Pole of the magnet. As a matter of fact, very interestingly, notice if I keep switching the polarity of the magnet, something very interesting happens to the compass needle. It begins to move almost as if it was periodically spinning. This, we will see later, is the basis of how we can make an electric motor. This is exactly what Faraday's law of induction says is possible when you have changing and alternating magnetic field. So we're going to be exploring that a little further later. Play a little bit with a coil and a solenoid. What you see on this PhET simulation is that I have a conducting loop of material connected to the poles of a battery. Now I have a compass over here where I can measure the magnetic field, and you see when I move this compass around, there's no magnetic field, and that's because if you'll notice that my battery, I have it set at 0 volts. So for my 0 volt battery, let me now turn the battery on so that I have a flow of current in that conductor. Now the blue little dots are indications of the flow of electrons. So the electrons you can see are coming up from the bottom of the loop and flowing into the battery. But keep in mind that the current is not the flow of positive charge. The current, I'm sorry, scratch that. The current is not the flow of negative charge. The current is the movement of a positive charge. So even though these electrons are moving in the direction you see on this schematic, current is flowing in the exact opposite direction. So what that means is that the current is coming out of the top of the loop. The current is going in to the bottom of the loop. Now if I bring the magnet, the compass close to it, you will notice the field lines are such that the compass needle inside the loop has the south pole of the magnet pointing towards the center of the loop. If I take it around to the other side, now I have the north pole of the magnet pointing towards the center of the loop. So the field lines for the loop internal to it, as you can see I move my cursor, is that the field is pointing to the right, coming out of this loop with the positive charge coming out of the top of the loop, positive charge going into the bottom of the loop. Use your right hand, point your thumb coming out of the top of the loop, and notice your fingers curl to the right inside the loop. Put your thumb going into the bottom of the loop and still inside the loop. your thumb points so that your fingers are coming to the right. Now I can come over here and pick the so-called field meter, and it indicates the strength of this field. Notice when I'm far from the loop, I'm getting a field strength of just a 0.8 Gauss. Now a Gauss is 10 to the minus 4 Tesla. So in the SI unit, that'd be 8 times 10 to the minus 5 Tesla. That's 0.8 Gauss. As I move closer, notice the field strength goes up dramatically. When I get inside the loop, the field strength is measured at 75 Gauss, which again would be 7.5 times 10 to the minus 3 Tesla. Now, interestingly, I could calculate the parameters of this with that formula B equals I mu 0 over R. If I knew the radius of the coil, I can't believe they don't have you do this on this. I would have, if I made this lab, I would have made you do that. The radius of the coil, the current flowing in it, we know the voltage, we don't know the current. But if we knew the current flowing through the wire, we knew the loop radius, we could plug in to B equals mu I over R, and we would get 75 Gauss. Actually, we'd probably get it in Tesla. We'd get 7.5 times 10 to the minus 3 Tesla for that calculation. Now, what I can do next is change the parameters of this loop in several ways. Notice if I switch the polarity of the battery, meaning I flip it over so it's now 10 volts in the opposite direction. Now you will note that the compass needles have flipped polarity so that the north pole is coming facing to the left. Now how I can verify that using the right-hand rule, again, I got to cheat a little bit. Electrons in blue are flowing, if you like, down the loop. That means the current is coming up the loop. That means the current is coming out at the bottom of the loop. And if I curl my fingers around, my thumb coming out would mean inside the loop, my fingers are pointing to the left. My current is going into the top of the loop, even though electrons are flowing down from that point. The current is going into the top at that point. So again, my fingers would curl so that the field is pointing to the left. If I move my compass over to the other side, you will see that again, that's indicating the direction of a south pointing arrow, if you like, on the other side. Now, another thing I can do is I can take for my simulation and add loops to this. Remember, for one loop, I'm getting a field of 75 Gauss. If I put two loops now, and the current is flowing through each of these loops, each of those coils will be generating 75 Gauss. So now, internal, I have 150 Gauss. Now, maybe something else you should notice is that it also gives you the components of the magnetic field, gives you the X and Y components. The magnetic field is entirely in the X direction. It is entirely pointing to the left in the X direction. By is 0. And notice it's making an angle theta with the X-axis of 180 degrees, meaning from the positive X-axis, this field vector would be pointing 180 degrees. So I switch the polarity. Watch what happens at an angle. I'm going to grab my arrow up here. Whoa, I didn't mean to do that. I meant to switch that. I have now a 0 degree angle because the magnetic field is now inside the coils to the right. It's 150 Gauss of magnitude. It's entirely in the X direction, making a 0 degree angle with the positive X-axis. Now notice what happens if I increase the loops to 3. I have 3 times the field strength of one coil, now 225 Gauss. If I increase it to 4, I have 4 times the field strength, or a total of 300 Gauss coming from those coils. Great, Faraday's law of induction. Let's take the case here of a primary on the left and a secondary on the right. The primary is a conductor connected to a power supply. Right now, the power supply is on 0 volts. If I move the primary into the secondary, you'll notice I'm generating no current in the secondary because there's no current in the primary. The blue dots are indicating the direction of motion of the electrons that are present. So let me do this. Let me turn the battery on, and notice it is now generating a steady flowing current. Remember, the blue direction of flow is the flow of electrons. The current is actually the opposite of the flow of electrons. So the current would be moving down the loop. So I would have a circle with a dot coming out at the top. I'd have a circle with an X going in at the bottom to indicate the direction of current flow. So that would mean I have inside the loops of the primary, inside the turns of it, I would have the the magnetic field pointing to the right. Now notice the weird phenomenon when I move this into the secondary loop. Notice how the light instantaneously flashes on, but then stops. So the light is on, and then it stops. This is because Faraday's induction occurs when you have changing magnetic field. The primary circuit is generating, as the charge is flowing now, a constant electric field. I'm sorry, scratch that. Constant magnetic field. With a constant magnetic field, there's no change in flux inside this coil loop. As long as the magnetic field is constant from the primary, the flux is constant in the loop. So delta phi, delta t is 0. So EMF is 0 because delta phi, delta t is 0 because phi is not changing with this constant magnetic field of the coils. Now let me move it quickly out, and you will note that the light flashes on only for a second, because the moment I stop the coils, again, the magnetic flux is constant within that loop of the secondary, so there's no delta phi, delta t. Once I start moving it, notice the light bulb is coming on. I have a constantly changing flux as I move the primary through the secondary. As it gets closer to the secondary, the flux is going up. As it goes away from the secondary, the flux is going down. As long as there's a change in flux through the secondary coil conductor, there is a generated EMF, or electromotive force voltage current, in the secondary circuit. Again, I can zoom it in there and stop. There's no current now while that it's, because I have constant flux in there. As I begin to move it, though, immediately there's a change in flux. Now notice that I can move this more and more rapidly. Notice they're trying to make the light bulb look more and more intense as I move it more and more rapidly, because the more and more quickly I'm moving it, then the delta phi delta t is getting bigger. I'm moving it, delta t is getting smaller. That means the E expression is getting bigger when I do things like that. Now the other thing I can do is I can up the number of turns. Right now I have 1 loop in my solenoid. I can go all the way up to 4 loops in my solenoid. Whoops, I didn't. Let me go to, it doesn't have 4 loops. It only has 1. Oh, it's changing the coils on the primary, sorry. I didn't realize I was changing the coils on the primary. Well, notice when I change the coils on the primary, then I'm going to get less. Notice I have a really hard time, even when I'm moving it rapidly. I'm not generating the huge brightness in the secondary. Now let me again up those loops to 4. Now let me move this. Notice how much brighter, as indicated by the rays coming off the light bulb, that I can make for the brightness of the light when I change the flux within the secondary. Now again, move it in, change of flux, light current flows, stationary charge, constant flux, no delta phi delta t, no current flowing. So let's demonstrate Lenz's law on a conducting loop. Here I have a bar magnet, so I'm going to use my PhET simulator to see what happens again when I move the bar magnet. We talked about this a little earlier. I move the bar magnet and notice I'm generating a current in the loops. Now, what the power company does is they use a steam engine or coal-powered turbines, and they literally move magnets back and forth, back and forth. Actually, they move the coils. They don't move the magnets. They're too heavy. So they keep the magnets stationary, they move the coils, and then they do this at a certain rate and speed, and they generate a nice alternating current for you. But let's analyze this according to Lenz's law. Now, notice when I move the north pole towards the coil, you'll see the light comes on, the blue dots move down. The blue dots are the direction of motion of the electrons, and I agree that's annoying, but that's not the direction of current flow. Current is flowing opposite the direction of the motion of the electrons. So when the north pole moves towards, the blue dots come down. That means the current is going in at the top. So if I point my thumb in at the top, that's the direction of current. This is because inside the loops, the coil itself is making magnetic flux in opposition to the north field lines that are coming at it. The North Pole has north field lines heading towards the loop. When I move this towards it, the coil says, no, 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 you're increasing my north field lines. I want opposition. So I will have my current going in at the top so that inside the coil, I'm generating a magnetic field pointing to the left to oppose the gain in magnetic field from the bar. So the current moves in at the top, even though the dots are going down. It moves in at the top, and it comes out at the bottom when I move the north pole towards the coil. Now, when I pull the coil, the bar away, notice now the dots are moving up the page. I am decreasing the north lines in the loop. The coil itself will increase north lines because of my action. To increase north lines, that means the current has to be, remember, the dots are moving up as I pull N away. That means the current is flowing in at the bottom. Point your thumb at the bottom in the direction in, and you will notice that my fingers point to the left now. I need to increase my north pole in order to pull that off. So that will be the action that I take when I do such thing. Okay, now can I flip the polarity of the magnet? Yes, I can. Now I have the south pole pointing towards the loop. When I move the south pole in, notice the dots move up. The dots move up mean current moves down. Current is going in at the bottom of the page. So current going in at the bottom of the page, point my thumb in the direction of current. That is again going in at the bottom of the page. That means that my field lines induced in the coil are pointing to the right because the field lines I'm adding from the magnet are pointing to the left. Remember, the field lines point in towards the south pole. So since I'm increasing the in towards the south pole field lines as I move towards the coil, it makes out to the right field lines itself, so it has a current induced going in at the bottom. Now, again, obviously, pull the south pole away. Notice as I pull the south pole away, dots moving down, current moving up, current moving in at the top, field lines going to the left induced in the coil. That's because I'm pulling more field lines to the left away as I move the South Pole away.